Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. So far in the numerical methods, we used elimination methods to find the optimum solution of single variable and constraint optimization problems. In this, there were 4 bracketing methods and 4 region elimination methods. The bracketing methods helped us to quickly bracket the optimum solution, and the region elimination method helped us to obtain the optimum solution with certain precision. In all these methods, we use the objective function values to reach closer to the optimum solution and observed that the Fibonacci and golden section search methods could reach closer to the optimum solution in less number of objective function evaluations. Today we are going to start discussion on some other methods that are generally considered more efficient than the Fibonacci and golden section search type of methods. These methods are collectively known as interpolation methods, and these methods may or may not require derivatives. So let's start with some of those methods, and in the next couple of lectures we'll be covering all the related methods. The interpolation method uses the magnitude of the function value while identifying a new point. And in today's discussion, we are going to discuss 2 methods where we are going to approximate the given objective function as a standard quadratic or cubic function to solve the optimization problem and reach closer to the optimum solution. So first we are going to discuss about the quadratic interpolation method. If we have a function which can be represented as shown in this image, we can always fit in a quadratic equation which is passing through some known points. Suppose these 3 are the known points, and if we fit in a quadratic equation which is going to be like this, and in the quadratic equation we can easily find out the minimum point. So suppose for the quadratic equation the minimum point is here, then we get a new point and we evaluate the actual objective function value at this particular point. So we'll get the function value as this, and when we compare the function values of the other 3 points which we already used to develop the quadratic equation, we can easily neglect 1 or 2, or we can easily eliminate one of the point which is not that good in yielding the objective function value. Then once we eliminate one of the point, we are now again have 3 points which we can use to fit a quadratic equation, and we can find the optimum solution from there, and the process goes on till we find that there is no improvement in the solution process. So let's look into the quadratic function. A generally quadratic function can be represented by an equation format like this, where we have 3 coefficients, this q0, q1 and q2. If we want to solve this quadratic function to obtain the 3 coefficient, we can do that by finding the function values at three different locations. So if we say these three sets of x and corresponding fx, the function values, are known for the objective function, then with those sets of values we can easily find out the coefficient q0 as the f of x1, the first point, q1 with the help of the 2 points, and q2 with the help of the 3 points which is shown here. Once we do this and fit into this quadratic function and try to optimize that function, we can see that the optimum point is going to lie at this particular location. So this particular location is going to be my point for the given objective function to further investigate. Now this solution is valid if the second order derivative of the quadratic function at this optimum point is greater than 0, that is when the function is going to yield minimum in case of minimization problem. Or in other words, if we say that q2 is greater than 0, then we have the valid solution. And once we have the valid solution, we need to compare the function values at the 4 points. 3 we already know, the fourth point is the optimum point, and we can keep the best 3. The preferred option should be the best solution with a bracket on either side. If the best solution is at one edge, then we can store the best 3 solution and move forward. So let's look into the algorithm of the quadratic interpolation method. In this particular method, in the first step, we need to choose a point from where we want to start. We also need to select a very small number which represents the precision of the result we want to achieve. We need to select a step size s and then find out the second point using that step size. Once we do this, then we find out the function value at the 2 points x1 and x2. By comparing these two function values in the second step, we need to estimate the third point, which is x3. If we find that x2 is lesser than the x1 object, if we find that the function value at x2 is lesser than the function value at x1, then we are going in a direction where the objective function value is going to reduce. So we select the third point even further away from the second point, and that is why we are saying the third point is x1 plus 2s. If we find the other way, which means the objective function value at the second point x2 is larger than the objective function value at x1, then we need to go in the negative direction, and in that case my third point x3 is going to be x1 minus s. Once we find the x3, we need to evaluate the function value at that point. These two steps are needed if we do not have the bracket. By any chance, if we use the bracketing methods which we discussed earlier and already have found the bracket, then we can use the bracket information and choose x1 as one end of the bracket and x3 as the other end of the bracket, and in between we can choose another point x2 which will represent the intermediate point. Once we have these 3 points, the step 3 starts. This is where we are going to have these 3 points and we'll have the function values at those 3 points, and once we know that, we can easily estimate the optimum point based on the quadratic equation or the function I just discussed in the previous slide. So once we find that particular point, we need to evaluate the function value at that particular point. Then we need to see whether the minimum objective function value we have between the 3 points x1, x2 and x3 and the objective function value at the new point at xq star, the difference is going to be more than the precision or less than the precision. If it is more than the precision, we need to save the best points with 2 brackets on either side. If bracketing points are not available, for example the best point happened to be the edge point, then we have to save the best 3 points and relabel these points such that it is in a sequence. Once we do this, then we have to go to the step 3, which is here. So in there we have revised the x1, x2 and x3, and we are again going to recalculate the optimum point based on a quadratic function, and the process goes on until we find that the difference between the best objective function of the 3 available point and the new point is less or equal to the precision we want to achieve. Once we get to that point, we need to terminate the process and report the x corresponding to the minimum function value between the 3 and the final point, which is total 4 points for our answer. Now let us look into an example where we can show how this method works. If you recall, we used this particular function in our earlier methods, and in this case we are saying that our initial guess point starts at 0. If you recall, earlier we said the bracket is between 0 and 3. If we want to use this 0 and 3, we can easily use that 0 and 3 and as x1 and x3, and in between we can select an x2. So to give you a resemblance of that particular method, in this case I have chosen a step size of s equal to 1.5. Now if you look into the 3 points, we are going to get 0, 1.5 and 3, and for the precision I have set it to 0.2. Now at these 3 points we need to find out the objective function value, and these objective function values are indicated here. Based on these objective function values, we need to estimate the Q0, Q1, Q2 of the quadratic function, and based on this q0, q1, q2, we are going to find out the optimum point of the quadratic function, and that is going to be 1.216, and at that particular point the objective function value is going to be negative 32.64. At this point, if we try to estimate the error by looking into the minimum between x1, x2 and x3, the objective function value, we will find the minimum value is negative 41.28, and the new point is going to yield the objective function value of 32.64. The difference between these 2 points is going to be 8.64. Now it is very clear to us that the new point is yielding an objective function value which is better than at least one of the points which we had earlier. So we can revise those 3 points in such a way that we have the best point at the middle. So our best point is here, which is at the middle, x2, and it is bracketed by the 2 points. So here we can bracket it by 1.22, and we are retaining the 3. Then based on these 3 points and their function value, we can again estimate the q0, q1, q2, and from those we can estimate the optimum point on the quadratic function and its objective function value at that point for the problem which we are solving. So at this point now we'll see that the error has reduced to 4.28, and if we continue this process, we'll see that after a while our error can be reduced to 0.2 at this level. If you go one more step, the error is going to be 0.08, which is less than the error which we want to achieve. Hence we can stop right here. However, in this particular example, I have gone through 2 more steps to see how better we can get the result, and in this case you will see that our final output is going to be the best out of the 4 points. So we can see that the objective function value at x1 is negative 49.95, x2 is negative 49.98, x3 is 46, and this new point, it is negative 49.99. So this is the best point. Hence this is my x star, or the optimum point for the given objective function, and this is the objective function value, optimum objective function value. Now we'll look into this method through a graphical representation. So in this graphical representation, first the objective function which we have can be represented by this blue line. This is the objective function between 0 and 3. We had selected 3 points on this objective function, and those 3 points are, one is 0, 0, another is 1.5, and the third one is 3. Using these 3 points, if we want to fit a quadratic function, then that quadratic function is going to look like this orange line. And if we want to find out the optimum point of this quadratic function, we'll find that the optimum point is going to be at 1.216, which is going to be somewhere very close to here. At this point, if we find the objective value of our original function, which is going to be this. So if we compare the objective function value of this point, this point, this point, and this point, we can clearly see that the best objective function value still we have at this 1.5, and if we want to bracket this point, we can bracket it by this point and this point, which is 3 and 1.216. So in the second iteration, my x1 is going to be 1.216, which is here. This will remain as x2 and this will remain as x3. Once we do this and fit in the quadratic function, then we'll find the quadratic function is going to be of this gray line, and if we try to find out the optimum point of this quadratic function, we'll find that it is going to be at 1.664, which is somewhere here. So at this point, now if we look into the function value of the given objective function, which is here, and if we compare the objective function value of the 3 points, then we'll find out that the objective function value here is still better. Then we have the objective function value is going to be here. So the better objective function value is now here, and the bracketing points of this point are going to be this and this, which is here. So this is going to become my x2 and this will become my x1 in the next iteration, and this will remain as x3. Now with the help of these 3 points, if we try to fit a quadratic function, that is going to look like this yellow line. Once we fit into this quadratic function, and if we find out the optimum point, we'll see that the optimum point lies at 1.789, which is somewhere here. And at this point, if we look into our objective function value, which is here, is actually better than the previous objective function value, which was here. So it needs to be improved. My middle point, or the x2, is going to be this now, and the 2 bracket points are going to be this one. So this x2 will now become x1 and the x3 will remain as is, and this process will continue for certain iterations, and at the end we'll find out that the optimum point for the quadratic function is going to be 1.987, which is somewhere here. And at that point, if we look into the objective function value of the given problem, we'll find out that it is better and so far the best one, and that value is very close to -50, and that is our optimum function value for that point, and this point is going to be the optimum solution for the given objective function. Now in this method, if you look into, we only use the objective function value to evaluate and find out a point. We did not use the magnitude of that objective function value or the relative magnitude of the objective function values to decide a point. And in certain cases, certain function, we may find that the quadratic approximation of the given objective function may not be fitting very well, and it could be slower. So there is another method which is cubic interpolation method. In this case, we are going to use the cubic function to approximate the given objective function and try to find out the optimum solution. So if you are looking into the cubic function, it is going to be of this nature, and here we are going to have 4 coefficients, rather C0, C1, C2 and C3. So these 4 coefficients need at least 4 x points to find out their values. The other option is that we can use only 2 points with corresponding function value fx and the first order derivative f dash x at those 2 points. So let us see how we can do that. If we want to fit this cubic function and find out the optimum point in this cubic function, it can be noted that this optimum point xc star is going to be x2 if my mu value is equal to 0, or it is going to be somewhere between x2 and x1, the 2 points which we are using to define C0, C1, C2, C3. So in those 2 points, it is going to be between x2 and x1 by this margin, x2 minus mu times x2 minus x1, provided my mu value is between 0 and 1. It is very clear here, once mu becomes 0, then it will become x2. In case if I find that the mu value is greater than 1, then the optimum point lies at the first point, which is x1. So to calculate this mu value, we need to calculate first the z value or z value, and this can be obtained by using this particular formula. Then we need to estimate the w value, which can be estimated by this particular formula, and once we use those in the mu equation which is here, we can obtain the mu value, test it, see whether it is equal to 0 or whether it is between 0 and 1 or it is greater than 1. Once we do that, we can find out the appropriate optimum value here, which will be using it further like what we did for the quadratic function to come up with the new point.